One last thing with black holes. Now, to understand this idea, we're actually going to have to delve a little bit into quantum mechanics. Not too much, don't panic. One of the things that we learn in quantum mechanics is that there are certain properties that are tied together. Specifically, the more we know about one, the less we can know about the other. Probably the most famous of these is the Heisenberg uncertainty principle. The Heisenberg uncertainty principle relates momentum or motion to the position of a particle. The better you know the position, the less you can know the momentum or motion of that particle. You cannot know both the position and the motion perfectly at the same time. What this does is it allows a certain amount of fuzziness within the subatomic realm. You can't know everything perfectly all the time. Well, one of these relationships is between energy and time. And this fuzziness between energy and time allows for what we refer to as virtual pairs of particles, meaning that particles can pop into existence, and as long as we cannot measure them before they pop back out of existence, okay, so energy and mass are related, so we have energy and time, they don't appear long enough, then it's allowed by these weird ideas of quantum mechanics. Now, the reason why we refer to these as virtual pairs is because we always get the particle and its antiparticle equivalent. So, for example, if an electron pops into existence, an anti-electron or positron also pops into existence. And then, as long as they are destroyed, they disappear again before we could measure them, then it's allowed. Now, I realize this sounds really, really weird. However, we've actually done experiments, and this has to happen to explain the results we're getting. So yeah, it's weird. We have particles popping into and out of existence around us all the time, but because we can't notice it, it's fine. Anyway, if we have a virtual pair of particles, and one of them pops into existence inside the event horizon of the black hole, it's not going to be able to escape. But if its partner pops into existence outside the event horizon of the black hole, it is possible for it to escape. Now, if it does, then it goes from being a virtual particle into being a real particle. Because it couldn't find its companion, then it doesn't go away. It sticks around. So it goes from being virtual to being real. Now, when that happens, it has to gain mass. As long as it was a virtual particle, it didn't have to have mass, it was all fine. But now that we could actually detect it, it has to have mass. And the only way for it to gain mass is to steal it from the black hole. So when this particle zips off away from the black hole, it steals that little bit of mass from the black hole. In other words, the black hole's mass has reduced by just a tiny little bit. Now, this is the idea of black hole evaporation. These particles that will then be coming off of the black hole we refer to as Hawking radiation, named after Stephen Hawking, who kind of figured out all of these ideas in the 1970s. Now, we actually have a relationship between the mass of the black hole and its evaporation rate, how much of these particles are going to be streaming off. Specifically, a smaller black hole will evaporate faster, have a faster evaporation rate than a more massive black hole. Now, to give you a sense of scale of how long it takes for a black hole to evaporate, stellar mass black holes, the ones that have masses in line with a few times the mass of the sun to a few dozen times the mass of the sun, these will take 10 to the 62 years to evaporate. That is a 1 followed by 62 zeros. In other words, it's going to take a long time. The current age of the universe is around 10 to the 10 years. In other words, the universe is not old enough to have had any black holes evaporate completely and really even change that much. Now, for a supermassive black hole, the ones that we see at the center of galaxies, these will take 10 to the 80th years to evaporate. But even so, black holes are not eternal. Even a black hole will eventually evaporate.